Consider a triangle ABC with the midpoints of the sides labeled A', B', and C' as shown. If we draw the perpendicular bisectors of the sides at A' and B', they intersect at a point. If the third perpendicular bisector is drawn, will it also contain this point? The answer is yes. The three perpendicular bisectors are indeed concurrent. Will this be true for all triangles, or is this particular triangle just a special case? Before we animate the triangle to visually demonstrate that this triangle isn't just a special case, we'll cut off the perpendicular bisectors so that they're only drawn to their point of concurrency. This will make the picture easier to analyze. Now let's animate the triangle. Notice that as the shape of the triangle changes, the three perpendicular bisectors continue to be concurrent. Of course, this is not a proof that the row is concurrent, it's just a demonstration. To prove that the row is concurrent, we first note that any two of them must surely intersect somewhere, since no two of them can be parallel. So we draw the bisectors of sides BC and AC to their point of intersection. We label that point O. Now what remains to be shown is that O lies on the perpendicular bisector of side AB as well. To prove this, note first that O must be equidistant from points B and C, since it lies on the perpendicular bisector of segment BC. So we draw OB and OC and mark them as congruent. Since O is also on the perpendicular bisector of segment AC, it must be equidistant from points A and C as well. So we draw OA and mark it congruent to OC. Since OA and OB are both congruent to OC, they must be congruent to each other. Thus O is equidistant from A and B, and so we can conclude that O is indeed on the perpendicular bisector of side AB, since any point that is equidistant from the endpoints of a segment must be on the perpendicular bisector of that segment. Thus the three perpendicular bisectors are concurrent. There's more to be said about point O. Note that since OA, OB, and OC are congruent, it must be that points A, B, and C all lie on the same circle centered at O. This circle is called the circumcircle of triangle ABC, and point O is called the circumcenter of the triangle. Notice that we have just proven a famous theorem in geometry, that there exists a circle that passes through any three non-collinear points. We not only know that such a circle exists for any 3 points now, but we also know how to construct it along with its center. Given any 3 non-collinear points, we can construct a circle through them by drawing 2 sides of the triangle determined by these 3 points, and drawing the perpendicular bisectors of these segments to their point of intersection. This gives us the center of the desired circle, and we then draw the circle centered at that point that goes through one of the original 3 points. This circle will go through the other 2 points as well. It's the circumcircle of the triangle determined by the original 3 points. You may have noticed some interesting things happening during the animation earlier. Let's take a closer look at that animation right now. The first thing to notice is that the circumcenter is not always in the interior of the triangle. Sometimes it's in the exterior of the triangle, sometimes it's in the interior, and sometimes it's actually a point on the triangle itself. It appears that the circumcenter lies on a side of the triangle when the triangle is a right triangle, and the side in question is the hypotenuse. Why should this be so? Well, consider the circumcircle, and remember the theorem that if an angle is inscribed in a circle, then the measure of the subtended arc is twice the measure of the inscribed angle. In the diagram, we have at point A a 90-degree angle inscribed in the circumcircle, so the measure of the subtended arc of the circle, from point C to point B, must be 180, or half the circle. Thus, CB is the diameter of the circle, and so it contains at its midpoint the center of the circle, O. When is the circumcenter in the exterior of the triangle? As you may have figured out by now, the circumcenter is in the exterior when the triangle is obtuse, and in the interior of the triangle when the triangle is acute. You can convince yourself of this on your own, again by considering the theorem regarding inscribed angles. We end this section with one last animation, to show what happens to the triangle as it approaches the degenerate case of a triangle where the 3 points are collinear. What would happen if we were to keep points B and C fixed, and move point A through line BC to the other side? Can you figure out what will happen to the circumcenter and circumcircle as A approaches segment BC and then crosses it? Pause now if you want time to think about it. The animation will continue in a few seconds. As point A approaches segment BC, angle A becomes more and more obtuse, and the measure of the subtended arc BC of the circle increases accordingly. The circumcenter is sent off into the horizon, so to speak, as the circumcircle grows infinitely big. When A, B, and C are collinear, we have a degenerate triangle, and we see the line through A, B, and C as the degenerate circumcircle, a sort of circle of infinite radius. When point A emerges on the other side of segment BC, the circumcenter emerges from the horizon but in the opposite direction from that in which it left. The line BC can be seen as one curve in a continuous family of curves, all of whose other members are genuinely circles. Another thing worth noting is that since the endpoints of side BC are fixed, so is the perpendicular bisector through A', and the circumcenter O simply goes off infinitely far on this line, only to re-emerge on the other side of this line after the degenerate case. Although strictly speaking there is no circumcenter in the degenerate case, one can imagine that the circumcenter in this case is at a special point on the horizon where the two rays emanating from A' meet. The idea that a point can go off in one direction of a line and then re-emerge from the other makes the idea of the line as a sort of circle appealing again. The relationship between circles and lines in geometry is very deep, and a full discussion of this relationship would lead to a discussion involving topology and other areas of mathematics beyond the scope of this section. This animation shows two situations in which the relationship is highlighted, but there are many more.